Hello dear students. So in the last class we have started with the geometry of Euclidean spaces. We have seen the definition of line, okay, then we have seen the definition of line segment, okay, we have also seen the definition of hyperplane, then we have seen the definition of hypersphere, and we have seen the definition of epsilon neighborhood of a point, right? Epsilon neighborhood of a point, right? And then similarly some other examples I wanted to show, some other definitions. So these are neighborhood we have done, then there's open set and closed set. So these things we can discuss. Interior point, yeah. So up to neighborhood I had done. So just let me quickly recall what is a line. Line in n-dimensional Euclidean space, line joining 2 points, say x comma y in e to the power n, okay, is say L equal to the set of all those lambda x plus 1 minus lambda y, okay, all those points which are of this type such that lambda belongs to real number. Okay. This collection of points is the straight line joining the points x and y. Okay. Then line segment joining these 2 points x comma y in e to the power n is say L equal to, it is also the collection of lambda x plus 1 minus lambda y, okay, but there is a restriction that lambda should be a real number which lies between 0 and 1. Okay. So if we restrict lambda to be lying between 0 and 1, then we get something called line segment. Okay. Then we have hyperplane. Hyperplane is the set of points satisfying the set of points, set of x, all those x inside Euclidean and dimensional space such that c times of x equal to z, okay, where c is also in n dimensional, c belongs to En and is a row vector, okay, row vector, and x is column vector, okay, column vector, and z belongs to real number, okay, so z is a real number, right? So set of all points which satisfy Cx equal to z. So in the expanded notation I can write the set of all those points which satisfy C1 x1 plus C2 x2, okay, plus dot 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 up to Cn xn equal to z, okay. This equation, the set of points which satisfy this equation is said to be hyperplane. Okay. Next we have seen what is the definition of a hypersphere. Okay, hypersphere. So what was that? It is the set of all those points x which satisfy x in e to the power n. So it is a hypersphere with center say a belongs to e to the power n and radius r, okay, radius r greater than 0. Okay, what is that? It is the set of all those x in e to the power n which satisfy mod of x minus a is equal to r. Okay, this was the definition, right? So this is called hypersphere. Okay. So what is this mod of x minus a? Where mod of x minus a, this is actually equal to root over of x1 minus a1 whole square plus x2 minus a2 whole square plus dot 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 up to xn minus an whole square. Okay. This quantity is called the distance between x and a. Okay. So, this distance is what makes up Euclidean space together with the vector space properties of R, okay, R to the power n, and the distance properties here. Together with that, it forms Euclidean n dimensional space. Okay. So, hypersphere is what we have done. Then epsilon neighborhood, okay, epsilon neighborhood of a point. So, just similar to what we have done in real analysis, epsilon neighborhood of a point is the hypersphere. So, epsilon neighborhood of, say, which one we had taken, say a, of a belongs to e to the power n is the set of points which lie inside the hypersphere. Okay. So, an epsilon neighborhood of the point A is defined to be the set of points inside the hypersphere. Okay. So, is the set of points in e to the power n that lie inside the hypersphere. Okay. Inside the hypersphere, this one with center A and radius epsilon, and radius epsilon. So, mathematically how do you denote it? We denote it this way: set of all those x in e to the power n such that mod of x minus a is strictly less than epsilon. Okay. Right. So, that is called epsilon neighborhood of a point A. Next, we have something called interior point of the set. Okay, let x subset of e to the power n, then a point small a belongs to x is said to be interior point of A, to be interior point of A if there exists an epsilon neighborhood. Okay. If there exists an epsilon neighborhood of A that lies in x. Okay. So, that is if there exists epsilon greater than 0 such that this set, the set of say x belongs to e to the power n such that mod of x minus a is less than epsilon, this is a subset of x. Okay. If this happens, then we say that it is an interior point of A. Okay. So, we can find a neighborhood. So, it is similar to what we have done in analysis, right? A neighborhood of a point, say A, it is actually the open interval a minus epsilon to a plus epsilon. Okay. So, we find out an open interval which contains the point A. Okay. So, this is what. So, here also an interior point of a set is if it contains an epsilon neighborhood containing the point A as center. Okay. So, yeah. So, by definition itself, any interior point of a set A of a set X is a point inside that set, because you have something like A minus A, this is equal to 0. Okay. 0 means the 0 vector. So, therefore, mod of this is always less than epsilon. Okay. So, A is always a member of neighborhood, epsilon neighborhood. Okay. A is also always a member of the epsilon neighborhood. Okay. So, interior point of A is has to be a point inside the set X. Okay. It cannot be something which is not there in X, right. then a point A belongs to e to the power n is said to be boundary point, is said to be a boundary point of some set x subset of e to the power n if. So, what happens when something is on the boundary? Okay, if you see the circle and if you consider this point on the boundary, then in that case if I take any epsilon neighborhood of this point, it will contain points of points outside the circle also, points inside the circle also. Okay, because this point is on the boundary, means that is basically the idea behind defining boundary of a set. Okay, so this is the geometrical thing, or yeah. So if we, from the geometrical viewpoint, if we consider points on the boundary of the circle and then we consider a hypersphere. So in 2 dimension, last day I told you hypersphere means a circle in 2 dimension. Okay, so if we consider an epsilon, so epsilon neighborhoods on the 2 dimensional space will be circles. Okay, so if we consider any circle with center at the boundary points, that circle will contain points inside also, points outside also. Okay, so that these points on the circumference of the circle are boundary points. Okay, so the motivation comes from this. So a point A belongs to e to the power n is said to be a boundary point of a x if every epsilon neighborhood of A contains points of x as well as x complement. Okay, x complement as well as its complement. Okay. So that is what, if every epsilon neighborhood about W contains the points of the set and also points not in the set. Okay. So according to definition, it is clear that a boundary point may or may not belong to the set. Okay, but an interior point must belong to the set. Okay. So a set is said to be closed if it contains all the boundary points of the set. Okay. And a set is said to be open set if it contains only the interior points of the set. Okay. So yeah, so let us write this one. So open set if means open set actually basically means every point in the set is an interior point. Okay, then we say that it's an open set. So a set capital X, which is a subset of e to the power n, is open, is said to be open, if every point of X is an interior point, of X. Okay, that is, okay, the meaning is, that is, for every small x belongs to capital X, there exists epsilon greater than 0 such that, or let us write it this way, for every small a belongs to capital X, there exists epsilon greater than 0 such that this hypersphere or the epsilon neighborhood such that x belongs to e to the power n satisfying mod of x minus a less than epsilon is a subset of X. Okay, there is some epsilon neighborhood of A. Okay, right. A set is said to be open if for every point A there is some epsilon neighborhood of A. Okay, so that means every point of the set is an open is an interior point. In that case, we say that it's an open set, right? And closed set is closed set. So a set is closed. Set is closed if it contains all its boundary points. It contains all its boundary points. Boundary points, right? So let us see some examples where we can get an idea about this boundary points and all. So let us consider the geometrical example only. Set of all those x1, x2 inside e to the power 2 that satisfy x1 square plus x2 square is less than or equal to, say, 4. Okay, and this. So what does it represent? This is the circular disc. Circular disc. Okay, with center origin and radius 2. Okay, circular disc with center origin, radius 2. So this circular disc actually is representing the interior as well as the boundary, the circumference of the circle. Okay, so this is a set which contains all its boundary points also. So this is a closed set. Okay, this is closed. Okay, so very similar to this, we can just write a general one. Say set of all those this x1, x2 up to xn in e to the power n that satisfy x1 square plus x2 square plus up to xn square is less than or equal to, say, 4, right, or say 6 or anything, something like a square, is also a closed set. Okay, this is a closed set. But if I write something like set of x1, x2 in e to the power 2 such that x1 square plus x2 square is strictly less than 4. Okay, in that case we have not included the boundary. Okay, so this becomes an open set. This is an open set. We have not included the boundary. Okay, we have included only the interior things, right? So this is an open set. Okay, why the earlier one is not open? Because if we take a point on the boundary, it will contain points of inside points inside the set also. It will also contain points outside. Okay, but for an open set, every point has to be an interior point. That means whatever there should exist an open sphere. There should exist this one epsilon neighborhood which lies entirely inside the set. Okay, but here for the boundary points here, okay, we cannot find any open that is epsilon neighborhood which lies completely inside the set. Okay, because every epsilon neighborhood here will contain points outside also. Okay, because if we take epsilon greater than 0, so it's something like this. So points here they will lie outside this circle. Okay, so this is a closed set, this is closed set, this is an open set. Okay, right. Okay, next we have a very important definition that is called a convex set. Okay, under what condition a set is said to be convex, right? So a set, say capital X, a subset of e to the power n, is said to be convex. So as you watch this video, you please try to note down the things that I am writing, otherwise you cannot understand. Okay, you have to learn these things by actually writing yourself. So a set X, a subset of e to the power n, is said to be convex if this one lambda times of x plus 1 minus lambda time of y, this belongs to x whenever or for all x y in capital X and 0 less than or equal to lambda less than or equal to 1. Okay, That means yeah, so a set is said to be convex if for any 2 points x1 x2 in the set, the line segment joining these 2 points is also in the set. Okay, that is a set capital X in e to the power n is convex if for any 2 points in e to the power n, say any 2 points x comma y in e to the power n, the line segment joining x and y is also inside x. Okay, right. So this is what in the earlier part I have written it symbolically. Okay, so a set X is said to be convex if lambda times of x plus 1 minus lambda times of y is in x whenever x and y are in x and 0 less than or equal to lambda less than or equal to 1. Okay, so this, if you remember, we had already noted that lambda x plus 1 minus lambda y, this this type of points, they represent points on the line joining x and y. Okay, so in particular, if we restrict to 0 less than or equal to lambda less than or equal to 1, then we get the line segment. Okay, so a set is said to be convex if the line segment joining any 2 points inside the set is also an element or means also lies completely inside the set X itself. Okay, so for example, let me just give you something that is not convex. Say we are considering E square, that is 2-dimensional space. Okay, then in that case, so in that case we have all the usual geometry that we have done. Okay, so can you say whether this is a convex set or not? Okay, say I write something like this, and then yeah, just let me. Okay, so this is just a diagram or figure that I have drawn, whether it is a convex set. Okay, by as per the definition we had given, a set is said to be convex if for any 2 points x and y in e to the power n, the line segment joining x and y is also inside x. Okay, so yeah, so what did I write? If no, sorry, a set X is said to be convex if for any 2 points x and y in x. Okay, not in e to the power n, sorry, that was a mistake. The earlier one I had written is correct, this one is incorrect, so please correct it. This is a point set X subset of this is subset of e to the power n is convex if for any 2 points x and y in x. Okay, in x, not in e to the power n. Okay, x is a subset of e to the power n, that is not a problem. Okay, this part is there. A set capital X which is a subset of e to the power n is convex if for any 2 points x and y in capital X, the line segment joining x and y is also inside capital X. Okay, right. So whether this type of diagram satisfies the convex properties or not. Okay, so if you observe carefully, if we take a point here and a point here and we try to draw a straight line passing through these 2 points, okay, then what will happen? A part of this straight line or a portion of this straight line will lie outside the given set. Okay, a portion of this straight line lies actually outside the given set. So this is not a convex set. Okay, however, if we draw it something like this, okay, so this is a quadrilateral. Okay, this becomes a convex set. Whatever lines you draw here, you see, whatever lines you try to draw, they all lie inside the set itself. Okay, so this is a convex set. What about circle? Is it a convex set or not? If we draw lines, whatever lines you draw inside the circle, this line segments, all these line segments will lie entirely inside C. Okay, so this is a convex set, this is a convex set, but this is not a convex set. Okay, right. Say for example, I give you some other problems, how we can determine this. Say exercise, show that the set A equal to the set of all those x y in e to the power n or e square that satisfy x plus twice y greater than or equal to 3. Okay, this is a convex set. Okay, so how we can show this? So it's very simple. We take 2 points inside this set, okay, and then we will try to show that they are convex combination. Okay, so this is what we call convex combination. This lambda x plus 1 minus lambda y provided 0 less than or equal to lambda less than or equal to 1. This is called convex combination. Okay, so how to show that this is a convex set? So let x1 y1, we have to take 2 points inside this set, and x2 y2 okay, belong to capital A, be any 2 points. Okay, be any points, right? So therefore, since they are points inside A, they will satisfy these conditions, right? Therefore, x1 plus twice y1, this is greater than or equal to 3, as well as and x2 plus twice y2, this is also greater than or equal to 0. Okay. Because these are elements in A, the elements in A satisfy this inequality. So since they are elements in A, they will also satisfy this inequality. Okay. Now I just want to check whether lambda x, okay, so here x is actually x1 y1 plus 1 minus lambda times of y means here x2 y2. Okay, so lambda into first point plus 1 minus lambda into second point, whether it belongs to this here or not. Okay, so how will you check? So first let us compute this. So under what condition this point will belong here? If it satisfies this property. Okay, so for that I need to identify the x coordinate, I need to identify the second coordinates. Okay, so let us identify. If we just simplify, this is lambda x1 plus 1 minus lambda x2, okay, and here also lambda y1 plus 1 minus lambda y2. Okay, this is the point. Okay, now so we can say that this point belongs to this set if it satisfies this particular property. Okay, so let us check whether it satisfies this property or not. Meanwhile, let us give it 1, this equation, inequation will give it 2. Okay, so now what I need to check? I need to check is this x1 plus 2 y1 greater than or equal to 3. That means this quantity plus 2 times of this quantity, this has to be greater than or equal to 3. Okay, so now lambda x1 plus 1 minus lambda times of x2, this quantity plus 2 times of lambda y1 plus 1 minus lambda times of y2. Okay, what is this? Let us compute. Okay, so I can write it simply as lambda times of x1 plus twice y1, right? If I take lambda common from both, and 1 minus lambda times of x2 plus 2 y2. Okay, we can always write it this way. Now x1 plus twice y1, this is already greater than or equal to 3. Okay, and 1 minus lambda times of x2 plus y2, this is already greater than or equal to 3. Okay, so this we have obtained by 1 and 2. Okay, so but what is this? This is actually 3 lambda plus 3 minus 3 lambda. Okay, so 3 lambda cancels out, this is actually 3. So here whatever equality we are writing, these equality actually represents that this quantity is equal to this quantity. Okay, so it doesn't mean that this is equal to this, that is incorrect. Okay, this equal to is already replaced by greater than or equal to. Okay, after that when I write equal to, it means that the previous line is equal to this line. Okay, so ultimately what I have shown that this coordinate plus 2 times of this coordinate is greater than or equal to 3. Hence this lambda times of x1 y1 plus 1 minus lambda times of x2 y2, this belongs to capital A. Okay. One thing I forgot to mention, let 0 less than or equal to lambda less than or equal to 1. Okay, under this condition, 0 less than or equal to lambda less than or equal to 1. Okay. So this belongs to this for all x1 y1 x2 y2, okay, x2 y2 inside capital A, okay, and 0 less than or equal to lambda less than or equal to 1. Okay. So for everything of that type, this is an element inside A. So this is a convex set. Okay, this is a convex set. So what does it represent geometrically? This particular set that I have written, if you can observe nicely, x plus twice y greater than or equal to 3. Okay, so it's something like x by 3 plus y by 3 by 2, okay, is greater than or equal to 3. So if we draw the diagram, it's x by 3, 1 2 3, okay, and y by 3 by 2, 1.5. Okay, so this was. So if I try to draw this diagram, so it will be something like this. Okay, and since 0 doesn't satisfy this, okay, so the region has to be away from 0. Okay, so this is the region, right, together with this negative part also, this is the region. Okay, so this is a convex set. Okay, so similarly you can try any other thing, something like this, say a set of all those xy inside, or say xyz inside e to the power 3, such that say ax plus by plus cz is less than or equal to say t, okay, less than or equal to some t, right. This is a convex set. Okay, so please try this exercise. Okay. Next, let us do some properties of sets, convex sets. So there is a theorem that intersection of two convex sets is convex. Okay, if we take the intersection of two convex sets, it is always going to be a convex set, right. Intersection of two convex sets is convex. Okay. So how to do it? So proof is very simple. Let a comma b be a subset of e to the power n. Okay. Right. A comma b subset of n, be two convex sets. Okay. Convex sets. Right. So I have to prove that to prove A intersection B is convex. Okay. Intersection of two convex set is convex. So first of all, we will take something like let x comma y belongs to A intersection B. Okay, be any points. So then x comma y belongs to A and x comma y belongs to B. Okay. Right, because x and y, they are the points in the intersection. So x and y will be in A also, x and y will be in B also. Okay. But A and B are convex. Okay. B are convex. It is given that A and B are convex sets, right? Convex sets. So lambda times of x plus 1 minus lambda times of y, this belongs to A, and lambda x plus 1 minus lambda y, this also belongs to B for all 0 less than or equal to lambda less than or equal to 1. Okay. So from here, thus we can say lambda x plus 1 minus lambda times of y, this is an element inside A intersection B. Okay. So ultimately we have shown that this intersection of two convex sets is convex. Okay, because I have started with two points in A intersection B, and then I have shown that their convex combination is also inside AB. Okay. So for all 0 less than or equal to lambda less than or equal to 1. Okay. So hence intersection of two convex sets is convex. Intersection of two convex sets is convex. Okay. Is convex. So you try to check whether the union of two convex sets is convex or not. Okay. So I think and there is another one, say intersection of arbitrary number of open sets, convex sets, that is also a convex set, right. So this was about convex set. There are certain other properties and theorems which we will do in the next class. So in the meanwhile, you please go through this lecture. Thank you.